and welcome. So we'll be looking at another example under contraflexure. All right. So for us to solve this, we are going to be starting with the summation of forces, that is in our y direction, to be equals to what? 0. We are taking upward force to be positive and the downward force to be negative. All right. So we are going to have our reaction at A plus our reaction at B to be equals to our downward force 2 plus, if you convert this uniform distributed load to a point load, because the uniform distributed load ranges from point C to point A and the total distance is 6. So we are going to convert that to a point load, which is going to be 2 multiplied by 6. So we are going to have reaction at A plus reaction at B to be equals to 2 plus 2 times 6 is 12, and 2 plus 12 is 14. So arrow A plus our reaction at B will be equals to 14. So this will be our equation number 1. So again, we'll be taking our moment about point A. So we are going to say summation of moment about point A should be equals to what? 0. All right. So don't forget, we are saying upward force positive. It means the moment created by our upward force will also be what? Positive. All right. So here we have an upward force here. Take a moment about this point, arrow A multiply by 4. So it's going to be arrow B rather multiply by 4. All right. So the rest is going to be downward force. So let's just say equals to. All right. So here we are going to have 2 multiplied by the total distance, which is 6. Then plus, here we are having a uniform distributed load. If we convert that to a point load, it's going to be 2 multiplied by the total distance, 2 multiplied by 6 also. Then it's going to act at where? Half of the what? Total distance. So it's going to be 6 divided by 2. All right. So this is going to be 4 arrow B, which will be equals to, here we are going to have 2 here 1, 2 here 3, right? 2 times 6 times 3 is 36. 2 times 6 is 12. So 12 plus 36 is 48. All right. So for us to get the value of our ROB, we are going to divide both sides by 4. So if you divide both sides by 4, our reaction at B will be equals to 12 kilonewton. All right. So for us to get our reaction at A, it's going to be 14 minus RB. That is 14 minus 12, which is 2. So it shows that our reaction at A will be equals to 2 kilonewton. All right. So now the next thing we are going to be doing is to calculate the shear force at to do the shear force calculation. All right. So let's go with shear force calculation. All right. So now the shear force at point A, point C rather. The shear force at point C. Here we are having just one shear force at point C, which is what? 2. But don't forget, our downward force is what? Negative. So it's going to be -2. So it's going to be -2 kilonewton. All right. So the shear force at point B now. All right. So you stand at point B. You stand at point B. If to this side, to the right hand side, we have -2, and we also have a uniform distributed load, and we also have this force here. All right. So the first thing here is -2. So it's going to be -2. Then we have a uniform distributed load. Uniform distributed load is the weight is 2. So if we convert that to a point load, it's going to be 2 times that is 2 times 2. That is 2 times 2. That is -4. All right. So here we are going to have another force here, that is the upward one, which is going to be plus what? Plus ROB. Our ROB is 12. So it's going to be 12. All right. So if you look at this now, this will be equals to -2 minus -4. That is -6. -6 plus 12. That is 6. So we are going to have 6 kilonewton. All right. So that is what we are going to have. All right. So the meaning of this is this. I love to explain this concept well. Now at point B, we are having 2 downward forces, right? Which is -2 minus -4. That is, this downward force here and the downward force we are going to have when we convert this uniform distributed load between this point and this point to downward force, which is negative, is going to be -2 multiplied by total distance, which is 2, is going to give us negative what? 4. So now -2 minus -2, that is going to give us what? Negative what? 6. That is the first force on our shear force. That is going to change from -6 now. So now, by the time you now add the effect of the upward force here, which is 12, is going to change from -6 to what? To +6. I hope you understand that. So I'm supposed to say -2 minus -4, which is, let me just write it in a proper way that I love writing it. So this will be -6 plus 12, so which is going to be 6 kilonewton. All right. So now the next one is the shear force at point A. The shear force at point A, which will be equals to, all right, the shear force at point A is going to be the first, if you start at point A to this side, so we are going to have -2, all right, -2, then upward force here, which is plus RB. Our RB is nothing but what? Plus 12, and then the uniform distributed load that we have, so which is going to be -2 multiplied by the total distance, -2 multiplied by the total distance, which is 6. So everything here will be equals to -2 times 6, that is 12. If you convert to a point load, that is what you are going to have. So 12 here, we go with what we have here, so we'll be left with -2. So this is -2 kilonewton. I hope you understand this. So we are done with our shear force calculation. So the next one is our bending moment calculation. All right, so the bending moment at point C. So at point C, we only have a downward force but no distance to our right hand side, so this will be equals to 0. All right, so the bending moment at point B will be equals to, at point C, when you stand at point C here, we only have this force here. To our right, we don't have any distance. That is why it's equals to 0, because we know that moment is force times distance. So at point B now, we start at point B, we have a downward force here, so which is going to be -2 multiplied by total distance, which is going to be what? -4. All right, so we're going to have -2 multiplied by 2. All right, and again, we also have a uniform distributed load. I want to make that before. All right, so we also have a uniform distributed load. So now this uniform distributed load is going to be, if you convert to a point load, that is -2 multiplied by 2, that is -4. So I'm going to say plus -2 multiplied by 2 times the distance that is going to cover there is going to be 2 divided by 2. All right, so by the time you do this, -2 multiplied, and that is -4. Here we are going to have 2 divided by 2 is 1, -4. -4 plus -4, that is -8. So we are going to have -8 kilonewton meter. All right, so the bending moment at point A, bending moment at point A will be equals to, so all right, so without even solving anything, because we know that this is an overhanging beam, so the bending moment at point A here must be equals to what? 0. But if you want to do that, that is going to be 2 multiplied by the total distance, that is -2 multiplied by 6 plus RB multiplied by 4 minus 2 times the total distance, then times the distance is going to cover there. Okay, let me just write it for us. So we are going to have -2 multiplied by the total distance, which is 6, then plus RB multiplied by 4, and our RB is going to be what? 12 times 4. Then now the uniform distributed load, if you convert to a point load, we are taking moment about point A there, so it's going to be plus, that is minus rather, -2 multiplied by the total distance, which is 6, then times 6 divided by 2. All right, so if you do this, if you do all of this, it must be equals to what? It must be equals to 0. So that is what we are going to have. All right, So now the next thing we are going to do now is we are going to draw our shear force and bending moment diagram. So we'll just draw at the point we have moment, we'll draw the this thing downward. All right, so here is our reference line for our shear force. Here is our reference line for our bending moment. All right, above this line is positive, below is what? Negative. All right, so the shear force at point C is what? Negative 2. All right, so let's just take this place as negative 2. So all right, and the shear force at point B, don't forget we have two shear force at point B. The first one is negative 6. All right, so let me take this one upward. So let's take this ones as negative 2, and let's take this point here as negative 6. All right, so because there's a uniform distributed load there, we are going to use an inclined line to join these 2 points together. All right, so now when we now add the effect of this reaction at B to it, then it goes to what? 6. So now here, let's take this one as 6. All right, so let's take that as 6. All right, and the shear force at point A, the shear force at point A is negative 2. All right, so negative 2, let's just take this one as negative 2. All right, so now we are going to use an inclined line to join this point with this point as well. All right, so that's it. So now we can therefore shade. All right, so now this is positive, this is negative, this is also negative. All right, so now let's go for our bending moment diagram. So now at point C, we have bending moment to be 0, that is it. Then at point B, our bending moment is negative 8. So let's take this to be negative 8. All right, and at point A, bending moment is also 0. All right, now, so now, but we must have our maximum bending moment, right? Because we know that our shear force is equals to 0 here, right? And anywhere our shear force is equals to 0, that is it is at that point that we are going to have maximum bending moment. So at this point now, anywhere our line crosses this shear force line is the point that we are going to have our shear force to be 0. All right, so now if I draw a line from here down to the bending moment diagram, so we are going to draw a line from this point down. All right, so now at this point now, from this point to this point now, let's call this place to be what? Y. All right, so now or you can name this point to be E. Let's name this point to be let's say this is AE. All right, so now so we can therefore say the shear force at point E will be equals to, all right, so it's going to be equals to, so if you want to calculate this, you know, you can calculate your shear force either to the left or to the right, but it will be more easier if we just consider to this side. All right, so now we are going to have, don't forget we still have upward force to be positive, and the upward force we have there is our arrow A, so it's going to be arrow A. Then don't forget we are going to have a uniform distributed load, which the distance is between AE, which is what? Y. So for us to convert this uniform distributed load to a point load, it's going to be 2, because the weight of this uniform distributed load is 2. So it's going to be 2 multiplied by the distance. So it's going to be minus 2y, because it's going to become a downward force now. All right. So now, and we are going to equate this to be equals to 0. So as for us to get the distance at which our shear force is going to be equals to what? 0. All right, so now this is going to be arrow A. Our arrow A is nothing but what? Our arrow A is 2. So we are going to say 2 minus 2y will be equals to what? 0. So if we say 2 is equals to 2y. So for us to get the value of y, we divide both sides by 2. So y will be equals to 1 meter. So it shows that the value of y is what? 1. Alright, so now we can calculate the bending moment, the maximum bending moment at that point. So we can say bending moment at point E, which is also the same thing as maximum bending moment, is going to be, so at this point now, if we want to calculate the bending moment, it's going to be arrow A multiplied by what? The total distance, which is what? Y. So it's going to be arrow A multiplied by y, then again minus, if we convert the uniform distributed load here between this point and this point to a point load, we are going to have -2 multiplied by y, -2y, then multiplied by what? Multiplied by y over 2. All right, so this will be equals to, now our arrow A is 2 multiplied by y. The value of y is 1 minus 2 multiplied by 1 over 2. That is what we have. So 1 times 1 is 1, 2 will go with 2, then 2 times 1 is 2. That is 2 minus 1 is 1. So it shows that the bending moment at point E is equals to what? 1, and which is also our maximum bending moment. So it shows that our bending moment will be maximum at 1. So don't forget, we have positive, and below is what? Negative. So here we are going to, let's just pick anywhere to be 1 here. So let's just say this is our 1. All right, so now the diagram is going to be like this, because we know that the bending moment at point B is nothing but what? 6, right? So we are going to connect 6 to 0. So this is going to look like this. All right, so again, we're going to have this to be like this. All right. All right, so that is what we are going to have. All right, so you can shade now. All right. All right. So here is negative and here is positive. All right. So now here is our shear force diagram. Here is our bending moment diagram. So the last thing we are going to calculate here is point of what? Contraflexure. All right. So the point of contraflexure. We said our point of contraflexure is nothing but the point where our bending moment is equals to 0 as it changes in sign, either from positive to negative or from negative to what? Positive. You can see at this point everything here is negative, then as you get to this point it starts changing to what? Positive. So this is our point of contraflexure. All right, so we are going to calculate at what distance is our point of contraflexure. So for us to do that, we are going to draw a line, straight line here. So for the purpose of your exam, you have to show your work with clarity. All right, so now this is it. So now from this point here to this point, let's call it to be y, to be x. All right, so let's name it to be s, and make sure your work is very neat. All right, so here to here is s. So if here to here is s, it means from this point to this point is going to be 4 minus s. So something like that. All right, so now we can calculate the moment either to the left or to the right. So let's just stand there and calculate our moment towards this side. All right, so here we are going to have arrow A multiplied by what? S. So we are going to have arrow A multiplied by S, arrow A multiplied by S, then the uniform distributed load here, convert it to a point load, that is -2 multiplied by total distance, which is S, -2s, then it's going to act at where? At S divided by 2. Everything here will be equals to what? 0, because the point of contraflexure is the point where bending moment is equals to 0 as it changes its sign. All right. So now here we have 2 here, we go with 2. Then we are going to be left with arrow S. What is our R? Sorry, our reaction at A, which is 2. So we are going to have 2S minus S squared equals to what? 0. Don't forget that S is common. We can factor out S into, then we are going to be left with 2 minus S equals to what? 0. So either S is equals to 0 or S is equals to what? Or S is equals to 2. All right. So, but our solution cannot be, S cannot be what? 0, because between this point A and this point, we must have a value that's not 0. So definitely our answer is going to be what? 2. So it shows that the point of contraflexure for this diagram is at a distance of 2 meters from point what? From point A. So that is going to be the solution. So let me just note this for you. So this is our point of contraflexure. All right, so that's it. So here hence the solution to the above question. I believe you understand and that you enjoy this class. Stay more for more interesting lecture. Thanks.